Here we go. Hello, welcome back to Introductory Astronomy. Today we're going to be venturing into the distant universe and talking about the universe as a whole. This is part of the more interesting parts of the course that really interests me. It's part of my research deals a little bit with cosmology, and I find it really cool to think about the entire universe and what can you say about it. So here's a picture of the some part of the distant universe, and we will be getting to what part that is later today. It seems like it could be of some moon that's nearby or something, but it's not. We'll get into the obligatory slides. This is Physics 1600, Introductory Astronomy at Michigan Technological University. So we'll be talking about the distant universe, and next time we'll be talking about the geometry of the universe. So I am Robert Nemroff, a professor here at Michigan Tech, and I am also one of the creators and editors and writers of the Astronomy Picture of the Day, which we will show pictures of, and we have shown pictures of throughout the course. So you probably statistically have stumbled across this on iTunes or on the web, but many people are taking this at Michigan Tech for credit this semester in fall 2008, and those people need to go here to get credit. I keep getting emails if people can go there anyway, and you can't, and I'm not releasing the quizzes. It's just too much work to do that. So there's actually people who want to take the quizzes who aren't in the course. I think I've mentioned that before too. Okay. So, but you are responsible for stuff if you're in the class. If you're not in the class, you're responsible for having fun. But if you're in the class, you're responsible for the lecture material, for the Wikipedia entries, for the APODs that are mentioned, and the APODs all the way from the beginning of the class through the, I think it's December 15th. And there's those fun quizzes, of which 1 to 9 I think are already due. I think 10 is due later today. So to find all the action, if you haven't gone to courses.mtu.edu yet, I'm not sure why you're still in the course. Okay. So let's get the big ball rolling, and here are the Wikipedia entries that will be covered today. Something called Olber's paradox, the cosmological principle, Hubble's law, the metric expansion of space, and the cosmic distance ladder will all be covered today as topics, and so you can go to Wikipedia and read up on them, except when it gets, particularly with this one, into math. So don't worry about the math. I'm interested in ideas, and particularly the ideas that I cover in class. Okay, so our universe. Let's consider our universe as a whole. Right now, let's consider it. All considered? Well, it's a big universe. There's lots of people in it, and that's only nearby. There's also planets near it that we know about, and that's nearby. And there's stars and galaxies. Oh my. How can we think about the entire universe? It's just too complex. So we have to make it simple. So when thinking about the universe as a whole, cosmologists generally try to consider only gross, vague parameters about the universe. For instance, if you were to take all mass, like you, me, chairs, planets, stars, and smear it out, then the universe would be homogeneous all over. And that's relatively simple enough to deal with. So when we talk about the universe as a whole, basically what our equations can tell us, the general relativistic equations, usually deal with the universe which is completely homogeneous and isotropic. So homogeneous means the same everywhere, and isotropic means the same in all directions. I guess homogeneous can mean the same locally. So here it is, smooth when averaged out. For example, Jell-O. Who's eaten Jell-O? Or should I say gelatin? It's relatively smooth, right? One part of the Jell-O generally is not much denser than the other part of the Jell-O. However, many of you have also eaten fruity Jell-O. Fruity Jell-O has chunks in it, just like our universe has galaxies in it. However, if you consider all of the Jell-O together, then you can sort of smooth out the fruit in the Jell-O and consider it all to be a little bit more dense than the Jell-O, a little bit less dense than the fruit altogether. So in that sense, the universe is homogeneous. Isotropic is the same in all directions. So right now, your universe is not the same in all directions, because if you look toward the monitor, you see my ugly face. But if you look in another direction, you see something else, hopefully more pleasant. However, if you were to turn off your monitor and turn out the room lights, it would be dark. And then it would be isotropic. The universe would then be the same for you in all directions. So is the universe the same for us in all directions? Well, if we go out, I mean, outside of monitors, and if we go out and look at the night sky, we see stars. If we look directly in the direction of a star, well, it's different in the direction of a star than another direction. If we look in the plane of our galaxy, then it's a little bit different there because there's lots of stars and they make a fuzzy Milky Way pattern. If we look at other galaxies, then, but if we just were to smear things out on the sky, so if you could take your smearing tool, like in Photoshop, and take it on the sky and smear out, fuzz all the pixels together, then they could be the same in all directions. And that would be isotropic. Okay. People have wondered about the universe for a long time. It's been, as long as there have been humans, so far as we know, people have wondered about the universe. It used to be, way, way long ago, the universe was essentially your village. And what was outside your village, there had been people who had ventured outside your village, sometimes a long way, and they would come back and tell stories, but most people wouldn't go beyond the next village or their village, you know. So they were happy with that, and that was sort of the universe. Then as time progressed, as humans became more sophisticated, as technology progressed, it became easier to travel far distances in a human lifetime. So ships became better, sailing on seas became better, and you could travel across seas. And since oceans are roughly the scale, and continents and oceans are roughly the scale of the Earth, the idea of the universe became essentially the Earth. The Earth was the universe. And there were these big shells around the universe that have things like stars and planets and the sun on them. And so then as time progressed and technology became more sophisticated, we realized that our Earth is not the center of the universe and that maybe our sun is. And so there are all these other points of light, but our sun is the center. And then as time progressed, we realized our sun is not unique. So it's not the center. So it used to be our village was the center, not the center. Then our Earth was the center, not the center. Then the sun was the center, not the center. So then for a while, our galaxy was the center, not the center, because as we heard last lecture, ending in around the 1930s, certainly in around the 1920s, people were debating whether our galaxy was the entire universe. And that turned out not to be true. So now we know there's lots of other galaxies. So our entire universe now is this big, big thing that's out there and contains many, many galaxies. Is it possible we will redefine our concept of universe? Quite possibly. So I think next lecture I'll be getting into multiverses and things like that, or the lecture after that. And our universe, which I'll have to define, is different from other possible universes. A working definition for the visible universe is everything that light can get to us from since the Big Bang. So that is the visible universe. Now there might be things outside of that, and equations of the universe, including from Einstein's general relativity, might explain those, might include those, but we don't have direct knowledge of them. They can't affect us because they're light, or things moving at the speed of light can't get to us from them. Okay, let's go back to Olbers, who was a few hundred years ago worried about things, and he asked a very simple question, which sounds really stupid. The simple question is, why is the sky dark at night? To which surely everybody around to him says, well, that's really stupid. Everyone knows it's dark at night. But he would say, just because everybody knows it doesn't mean it makes sense to me. So we wouldn't be talking about him unless he had some kind of a point. He would have just gone down in history as just another local lunatic. But he had something pretty clever. So he said that, so let's go to the next slide, that if you point in any direction, that direction goes through empty space, but if the universe is filled with stars, that direction should end on a star. Therefore, every direction should be as bright as the surface of a star. Now you're saying, well, wait a minute, faraway stars aren't bright. It's only the close by stars that are bright. But there becomes a difference between the total brightness of something and the surface brightness of something. So in our local universe, when you take the sun away, if you were to move the sun closer to us, its surface brightness would be exactly the same. It would just have a greater surface area. So those other stars that we see at night, particularly when we look from above the Earth's atmosphere, they have the same surface brightness as the sun. It's just that their surface area that we see, or angular area that we see, is very small. So the reason why stars are dim individually is because they're angularly very small, not because on their surface it appears any less bright. But that just is, so Olbers realized that, and he said, well, see, if you point in any direction and up on a star, then that star is going to have the same surface brightness as our sun, assuming that our stars are like the sun. So the sky, the night sky, should be lit up and be as bright as the sun. So what do you think of that? And people said, well, that sounds stupid, but I can't think of a reason why that's not true. So let me demonstrate this in this picture. Oops. So here we are. Let's say we are here in Action Central, and we just point in a random direction right to a star. Boing, hits a star. Same surface brightness. Now, let's cheat a little bit and try to point a little bit farther away. Let's try here. Whoops, hits a star. If the universe is infinite, you're not going to be able to find a direction that doesn't hit a star. That's what Olbers was saying. Here's a little movie that shows if you just think of any direction, eventually, as you consider stars further and further away, although this is sort of a fractal pattern, you will eventually find a star there. And that gets annoying. It's actually fun to see the first few times. Then it gets annoying. Okay. So this assumes that the Olbers paradox of the sky, why isn't the sky dark at night, assumes the universe is infinite. It assumes that all stars have the same surface brightness, and the surface brightness does not depend on distance. Okay. As an aside, why is the sky bright during the day? Well, what you're seeing during the day, with the blue sky in particular, and even white clouds, is essentially sunlight. So it's all repackaged sunlight. It's bounced off, if it's blue, it's bounced off of things in air and aerosols in the Earth's atmosphere, and if it's a cloud, then it's bouncing off of little water droplets. So that lights it up during the day. But at night, not sure. Not sure yet. Okay, so this again, this goes back to the slide that summarizes this. These are these two slides I showed. So here's another way of picturing it. Let's say that you go into a dense forest, an object which is somewhat common here in the Upper Peninsula of Michigan, where there's lots of forests. So let's say you just go out and into the forest. Now, you're just going to consider looking on your eyesight level. You're not going to look up or down, so it's just only eyesight level. So there are trees in every direction. So every direction you point is going to end in a tree. So if you were to take a tennis ball, say, and throw it, just spin around, close your eyes and throw it, and you could throw it right at your eye level, it'd hit a tree. There's no way. If you get one of those fancy laser pointers and you were to point it, it's going to hit a tree. If you go into a dense enough forest, every direction hits a tree. And therefore, since tree bark is usually kind of brown, although it reflects sunlight, you're going to be seeing essentially brown in every direction. That is like Olbers' paradox, except Olbers does it in 3 dimensions and with stars. So people wondered about this for a long time, meaning hundreds of years, and it's only been within the past 50 years or so that we've come to a clear understanding as to Olbers' paradox. The understanding is very interesting. First of all, we have to criticize, I guess, some of the assumptions that went into it, but it's really just learning about a universe. And we now know the universe is not infinite in size. The visible universe has a finite size, and that size is essentially the size that distances further than a photon that could get to us since the Big Bang aren't relevant. In that sense, the visible universe has a finite size. We also know now that the universe has a finite age. That's another possibility that could solve it, that if the universe is only finite in size, so if you went out in the forest and it was like not really a forest, if it was only like 3 trees and it was dark out at night, then the area around you wouldn't be brown because there would only be trees and few. That's the finite in size. Finite in age is a little bit like finite in size in that, let's see, yeah, it would just be all the trees, only out to a certain radius would there be trees because the universe didn't exist before that age. Here's something. We know about the universe much more than before. There's a lot of stuff called dust in the universe, and we've seen a lot of pretty pictures involving dark dust. So as I've mentioned, this dust is roughly the size of smoke dust if someone smokes, but there's lots of it out in the universe, made mostly out in cool places in the universe, molecular clouds in the envelopes of massive stars, cooler stars. So this dust is dispersed in the universe, but it's dark. So if we were in the middle of a molecular cloud, the universe would be really dark, and it wouldn't have anything to do with any of this. So one possibility is that the universe is just lots of dust out there that we didn't know about. Another possibility is that the light gets too redshifted to see. So maybe there are stars like, now that we know that as we go out into the universe in a relativistic cosmology, that light gets redshifted. So it moves toward the red end. So if you had a light that was only blue, if you had a flashlight and you put a blue cellophane over it, and you dispatched somebody out in the universe, way out in the universe, and they were to stop well far away, then their blue cellophane flashlight, if they go far enough, would appear to you to be red. And as they go even further, it would move into the infrared. And therein lies the redshift possibility of solving Olber's paradox. Maybe there's lots of stars like our sun, but their light gets so redshifted that it just falls out of the visible band so that we don't see it much anymore. So, given these four possibilities, which do you in the studio audience, and you at home can vote too. So why don't we take a minute where no one shows what they think the answer is, so people at home can go, And it's good to get the brain cells churning. And okay, so before you fall asleep, let's poll the studio audience and see which of these people think is most correct or completely correct. Who thinks it is the universe is finite in age? What? You can vote for as many as you want, yeah. Who thinks okay. Okay, 3 for finite in, what did I say, age or size?
Age.
I said age, okay. So we have 75%. How about finite in size? How about dust blocks out most of the universe? How about light gets too redshifted to see? Okay, well, okay, people are pretty savvy here. But all of those have effect, but it's the finite age of the universe that's really the most important factor. So there are lots in this way of looking at things. So let's say the universe is filled with stars. Oops, hit the wrong thing. So I'm going to put lots of stars all over the screen, and we're in the center. What? Yeah. So now there's a person in the center who says hi. Hard to read that. And so basically, light can't get to us from out there. So these stars may exist, but their light didn't get to us yet. That is probably the one of the major factors due to the finite age, which is related to the finite size. Also, their light is significantly redshifted. But what's interesting is that many things in the early universe have very blue colors, or very purple colors, or and so those are redshifted into our wavelength bands. Also, the microwave background radiation, which we discussed and we'll discuss again, it could have been redshifted right into our visual band and could have been bright. So there is also a claim that that redshifting is important because it just happens to be so redshifted, the microwave background, into the microwave, which we can't see. If it would have been redshifted into the red band, the night sky would be bright in red. Okay. We do know also another interesting solution to Olber's paradox is that the background there are in every, it turns out that that Olber's was sort of wrong. The sky is dark at night, but it's not completely dark. It turns out that in every direction you point, and in every wavelength band you look, there is some amount of brightness. It's just not enough for humans to say, oh, that's bright in the visible. So you could pick a wavelength band, pick X-rays. You can pick that direction in the X-rays. And sure enough, if you draw a circle in the sky to a degree or so in that direction, there's going to be X-rays coming from that direction. There's going to be gamma rays. There's going to be radio waves from any direction. It's just variable amount, which is the most. And there's a peak in the microwave, which is why one of the reasons the microwave is so interesting. So Olber was sort of correct in wondering that after all. It was a very clever thing to wonder. So this is the microwave background that's been mentioned. This was taken by the COBE satellite, the Cosmic Background Explorer. And so even though the apod is from 2006, I believe this is about a decade old or more. And here we see a background that is false colored. It's roughly 3 degrees. Let's go to a color that's not. It's 3 degrees Kelvin, where 0 degrees Kelvin is essentially atoms that don't move. Yes, it's possible to get energy-absorbing atoms that potentially have negative Kelvin, but in terms of kinetic definitions of temperature, 0 degrees Kelvin is pretty cold, and so these photons, although photons always move at the speed of light locally, they're very less energetic than they were back when they were emitted, when they were emitting gamma rays back, 100,000 years after the Big Bang or so, a couple 100,000 years. But they left in the gamma rays then, or the hard X-rays, and they've come across the universe being redshifted all the time, and the sky is pretty uniform. Actually, I don't have the sky map. That gets a little bit off the topic. So it turns out, I don't know if I have it. Let me check the next slide. No. Okay, so it turns out that the microwave background is actually a little bit hotter in one direction than another. It's, to a first approximation, it's pretty much 3 degrees. Same abundance of photons, same energy photons in every direction. But if you look closely in one direction is somewhat hot, and the other direction is somewhat cold. I'll just make it an empty thing. So this is slightly hotter than 3 degrees. This is 3 plus degrees. And this is 3 minus degrees. That's because we think the Earth, but not really just the Earth, the Sun and our galaxy is moving with respect to the microwave background. And so the direction we move in due to relativistic aberration causes things to bunch up in the sky. So if you stood still with respect to a background radiation field, so it's the same in all directions, and then you started moving quickly toward one direction, the radiation would tend to bunch up in the sky and would be hotter and more dense in the direction you're moving. That's relativistic aberration, and colder and less dense in the opposite direction. So if you had a field of stars all around that's uniform, and then you start to move really, really quickly near the speed of light, the stars will seem to bunch up in front of you. And behind you will be relatively few stars. And that's a well-known effect. So we see ourselves moving through the microwave background, but then we can take that out because it's relatively easy to model, and it comes right off pretty easily. So once you take that off, you see this map here that I've shown was found by Kobe. And there's only slight differences, like 1 part in 10 to the 5 differences between the temperature. It's actually determined to be 2.7 degrees. Decimal place, decimal place, decimal, decimal place. And only when you get out to, I think, this decimal place or so, is there any slight difference between here and here. Let's go to another. This is in the infrared. Now, these black circles are just where there's no data. But where they do have data, there's infrared brightness that slightly varies on the sky. Okay, this is also by Kobe, but I think this is at a different wavelength. This is toward the infrared. And here you see the plane of our galaxy. But here you see the universe is, infrared in all directions. Here we are in the X-ray. Some of these, as we've discussed, are local structures, but we get away from the local structures, away from the galactic plane, which is here. We just look, let's say, out here. There's X-rays. So what causes those is sometimes cause of some debate. There could be lots of dentistry going on in the universe. But we think now that it's actually, as I mentioned before, has to do with active galactic nuclei. Okay, so jumping a little bit to another section of the universe, another topic in the universe, off of Olber's paradox. In the beginning of last century, we didn't know whether our galaxy was the entire universe or not. And in the 1930s, in dramatic fashion, Edwin Hubble then discovered, by the way, when I looked him up on Wikipedia, I was surprised to learn that they didn't mention that he was an Olympic basketball player. Although he was quite into sports, I might have been wrong about saying he was an Olympic basketball player. Sorry about that. I'll check into that more, though. But anyway, when he was past his athletic career and into being a professional astronomer up on Mount Wilson, I believe, looking through the biggest telescopes of the day, which helped. His eyesight wasn't so good as so he could revolutionize science by himself. He needed big telescopes, which is fine because other people had access to the telescopes and he was very clever in using them. So he went to try to solve this mystery as to whether our universe was our galaxy was the only galaxy in the universe, and found the Andromeda galaxy had Cepheid variables, and so it was another galaxy. And then he started looking out at the other spiral nebulae, which were known. There were lots of these spirally things on the sky. We just didn't know for sure what they were. Once it was determined that they were other galaxies and data and technology started getting better, he was able to get spectra of these spiral nebulae, which are external galaxies, and find out try to identify the spectral lines in there. So galaxies are made of elements. And the assumption is they're made of the same elements that we're made out of, which is a good assumption. Turns out we know now the universe is almost all hydrogen, and the next comes helium, and there's trace amounts of stuff like us. That's in baryonic matter. We'll learn later that the universe is not even mostly that. It's mostly dark energy, and past that it's mostly dark matter, and past that it's baryonic matter, and past that it's hydrogen mostly. But so we're just a fraction of a fraction here. But looking at that fraction of a fraction, we expect it to emit in certain ways that we know in our laboratory. So we can play with hydrogen and helium and all these elements in our laboratory, and we can give them extra electrons, we can ionize them and watch them fall back. And we know, just like looking at the sun and the stars, we know, nearby stars, we know what spectral lines we expect from them. So we look at these nearby galaxies, or Hubble did, and he looked at these nearby galaxies, and he saw very familiar sets of spectral lines. Oh, I know these. The problem was they weren't exactly where he thought they should be. They were more red-shifted. They were shifted to the red. And there seemed to be a correlation. The smaller the galaxy, the more distant the galaxy, the more the redshift is. Explaining the redshift is just the velocity of recession, you can then make a relation, and you can say the velocity of recession is directly proportional, is equal to distance times, it's proportional to, and here's the proportionality constant. And since he came up with the proportionality constant, it gets named for him. It's called Hubble's constant. This works in the nearby universe. If you go far away in the universe, there's no longer a linear relation between velocity. Linear means just one number times the other. It gets more complicated. But in the nearby universe, this works fine. So v is the galaxy velocity, d is the galaxy distance. It turns out when you go out in the universe, velocities can appear to go faster than the speed of light. How can that be? Distances are ambiguously defined and can be defined in any number of ways, and you get different distances. But in the nearby universe, you don't have those problems so much. More distant galaxies are moving away faster, Hubble found, and that is why we say our universe is expanding. Now, it's not all the galaxies are moving away from us. After you get past a certain distance, then yeah, all of them are moving away from us. But the Andromeda galaxy is slightly moving toward us. So doesn't it know? Well, it so happens that the gravitational attraction of our galaxy toward, and other galaxies toward the Andromeda galaxy dwarfs what's called the Hubble expansion. So nearby galaxies can gravitationally attract each other and then pull them out of what's called the Hubble flow, which is the expanding universe. But as you go far enough away from any individual galaxy or from us, then you're fine. You don't have to worry about that. Now, let's see. Remember, this works according to the cosmological principle, which we talked about briefly. Let's go back to that. In the cosmological principle, the universe is not only homogeneous and isotropic, but appears so from every place in the universe. So if we go out to someplace else in the universe, it's going to appear the same way. We don't live in a special place in the universe. So one of the things about the analogy of we used to live in a village, and this village was the center, that was a special place. But it turns out there's all these other villages, and they consider themselves the center of the universe just the same. And then we were on planet Earth, and that was sort of the center. Well, actually, it's the center of the Earth that would be the center. And the sun was the center, but then other stars consider themselves to be the center. So we now think that we are not a unique center to the universe. That there's lots of places, every place in the universe can be considered to be a center, but there's no unique place. So the Hubble expansion, so we'll go back. The Hubble expansion is seen from every place in the universe. It's not unique to us. We don't just happen to be in the center of a universe that's expanding. So if you were to take, there's a couple ways of looking at this. If you were to take, let's say you were to start out in a race. Here we go. So here's a race. Here's the start line. I digress, but we're going to get someplace. So there's fast person, medium person, and a slow person. So the race starts, and the fast person zips out, and the medium person zips next, and the slow person is slowest. So if you're the medium, well, let's do a super slow and a super fast. So the super fast goes way up here, and the super slow goes way down here. So if you consider from the medium person's point of view, they look around them in the race, and they see this person, the fast person, moving faster than them, and the slow person moving slower than them. But from their point of view, the slow person is going in the opposite direction, and the fast person is moving in this direction. So they see themselves in the center of a Hubble flow. So the slow person then can look at the medium person moving faster than them and the super slow person, and they see the same thing. And the fast person sees the same thing. So it doesn't matter where you are in the race. Everybody sees the other people in the race dispersing from them. And the big group, the peloton of people, and if you're into bike terms, expands because everybody has a different velocity. And it doesn't matter where you are in that group, that you always see the group expand. Well, that's the way the Hubble's law is. We don't have to be at any center of the universe to see a Hubble law. We can see it from anywhere. One way to picture this is there's raisin bread. This is a big one. So picture raisin bread rising. And every raisin in the bread would be able to see other raisins as the bread expands, move away from them. Another way is to picture on the surface of a sphere that's being expanded. Or it could be a balloon that's being blown up. So here you have the balloon here, and here you have the balloon here, and this distance here and this distance here, they increase from 1 centimeter to 2 centimeters, and 2 centimeters goes to 4 centimeters. So all the distances between red spots here are increasing as the bubble expands. And all the distances, most of the distances between galaxies in our universe expand as the universe expands. So the distances between average galaxies are increasing, just like the red spots here. And even another way to do it, let's say you were to take a balloon, and on the surface of this balloon, you were to paint all these stars, and then you were to blow the balloon up. As the balloon becomes bigger and bigger, the average distance between stars grows. And the star sees other stars move away from them faster and faster the further away. Yet each star could consider itself to be the center of the balloon. But in this case, the center of the balloon needs another dimension to find it. It's because each point on the surface of this balloon could consider itself to be the center. So, in general relativistic cosmology, there is no center to the universe. Just like if you're confined to the surface of a balloon, there's no center to the balloon on the balloon. There is no Big Bang National Park. So I get email sometimes saying, well, where is the center of the universe? Why don't we look in that direction? According to general relativistic cosmology, as hypothesized by Albert Einstein and studied by many, many people since then, there is no Big Bang National Park where there's some black hole that you can go to or some direction you can look into. It's all the same. Everything looks the same and always did look, well, no, if it always looked the same, it would be the perfect cosmological principle, which we don't believe. But if you go to any place in the universe, you would see the same thing that you see right from us, pretty much, on the average. One way of picturing it also is that people think of the universe as an exploding golf ball. The exploding golf ball is more similar to what's called a Newtonian cosmology as opposed to general relativistic, which is the Einsteinian cosmology. And it's true, actually, that in an exploding golf ball, if you were to take points that are exploding out, they would see a Hubble's law. But you get problems with edges of the universe in that case. So the universe should not be considered an exploding golf ball. When there was a Big Bang, it shouldn't be considered there was this dense thing that you could stand outside and look at and then watch it explode. No, you have to be part of the explosion. You're confined to the surface of the balloon that's expanding. That's the best way we understand things, the most predictive way in Einsteinian general relativistic cosmology. Okay, so as I said before, Newtonian cosmology does have a center. But that would result in strange unseen forces to us now if Newtonian cosmology was completely correct. And also Newtonian cosmology would have to have some adaptation to Einsteinian principles because we know the speed of light is not infinite. Another thing is that you and I are not expanding. A misnomer is that, well, if the universe is expanding, then maybe I'm getting taller. And this applies not just to children. Maybe this desk is getting bigger. Maybe the Earth is getting bigger. And the answer to that is no. We have big forces pulling on us, mostly electromagnetic forces that are holding us together. Between local galaxies, the Andromeda galaxy and us, gravity does it. Gravity holds the Earth together. These things are much more powerful than any cosmological forces that might be acting. So something might have happened way long ago to cause the universe to expand. And there might be, as we'll talk about next lecture, or even a little bit this lecture, a dark energy out there, which has a slightly repulsive force everywhere. But it is completely dwarfed by our own electromagnetic and gravitational forces that we know about, local gravity. And so even though even though galaxies are moving away from us, galaxies themselves are not expanding. People are not expanding. There is a caveat to this. That there's something called phantom energy that we don't know exists, but could possibly exist. We'll talk about that later. But the standard thinking is that there's no there's no phantom energy, and so certainly in the past, there's nothing in the nearby past that needs that. That we're not expanding with the universe. It is the galaxies moving apart that is the expanding universe. Okay, so what is H0? Should be subscripted. What is the Hubble's constant? Well, Hubble actually got the idea right, but got the number wrong. He was looking at several different types of Cepheid variables, wasn't clear there were different types, calibrated it wrong. So in the past 20 years, there's been a very big push to get the Hubble's constant right. And we still have an annoyingly large error, but we're zooming in on the right answer only in the past few years, but based on primarily measurements from the Hubble Space Telescope. So we now believe that a good approximation for the Hubble's constant is 71 kilometers per second per megaparsec. So kilometers per second is something that you could measure your car going in. Although cars are so slow, you need an hour to actually, kilometers per hour is a better measure. Megaparsec is a distant unit, is a measurement of distance like light years. But there's 3.2 light years per parsec. So 3.2 light years is equal to 1 parsec. M means million, 10 to the 6. Professional astronomers still like to use parsec. I believe conceptually simpler is light year, but once something has some infrastructure involved in it, it's difficult to go away from it. As we know here in the United States, because we're stuck in the English system of units, and it's expensive to switch over to metric, even though I think just about everybody would agree that metric is better. I still think we should spend the money and switch over, although perhaps in today's economy it should wait till next year. The Hubble's relation can be distance equal velocity divided by Hubble's constant. So let's say you have something that has a velocity, you measure its redshift having a recessional velocity of 7,100 kilometers per second. So d would be equal to v over h, 0. 0 means it's the present value of the Hubble parameter, the Hubble's constant. So this would be 7,100 kilometers per second divided by 71, let's not worry about errors right now, kilometers per second per megaparsec. And that would give you 100 parsecs, equals 100 megaparsecs, which is a reasonably distant galaxy, actually still in the local universe. So that might come up in a quiz, maybe. So be sure to understand that. So here is a plot of local galaxies out to the local universe, distance in megaparsecs, velocity in kilometers per second. And so as Hubble, well, as we see nowadays, if you try to fit a recessional velocity of 50, it's too low, 100 is too high, although Hubble originally had over 100, I think. 67 seems to fit okay, but actually, as we get more and better data, 71 seems to be a little bit better, plus or minus 5. Which leads me to the cosmological distance ladder. So how do we know distances like this out to megaparsecs, distances out here? As you get further out in the universe, it gets harder and harder to know things. So we create something called the cosmological distance ladder, which pretty much says that we know the distances to things nearby because we have tape measures. And we know the distances to things in our solar system because we've sent things out there. And then things get fuzzy after that. But we can use the nearby stuff to measure. So we find something, let's say, that has both tape measure distance and another type of distance measure. And then we calibrate that next distance measure. And then as we look further out in the universe, we can't go out with the tape measure anymore. We can't even use whatever the secondary one was. And so we keep trying to calibrate the different distance measures as you go further out in the universe. So how do we know the distance to our sun? We can bounce radar off it. We know how fast the speed of light is. So we really know how far away our sun is. The nearest stars we know through something called parallax. So as our Earth goes around the sun, the nearby stars shift back and forth. And we know the distance to the sun, and we know general geometry. So if our sun is here and our Earth is here, and then our Earth is here, and the star appears to shift, we can get this angle exactly, and we can measure parallax, and we can measure the distances to nearby stars. And there's now spacecraft that do that even more accurately than ever before. Measuring distances to nearby stars, eventually we can measure the distance to star clusters, in particular open star clusters. Once we're in open star clusters, we can get their distance by main sequence fitting. Main sequence fitting, actually, we can even jump over that and get right to Cepheids at this point. And say we can now find star clusters, distances of star clusters that have Cepheids in them, and calibrate Cepheids. Now Cepheids, the longer they take to vary, the more bright they are. So if they appear dim and they're very bright, then we know they're far away, and we can calculate how far that is. So here is an open cluster. Here is a galaxy with Cepheids in it. So the next rung of the distance ladder might be considered supernovae. So now we try to find galaxies that have both Cepheids in them and supernova, and try to calibrate how bright those supernovas are. And so we can do that. And there's especially type 1a supernova that are very useful this way, are calibratable to standard candles. So they're all standard candle means all candles are the same, they get roughly the same brightness. So the nearest galaxies are Cepheid variables. Supernovas are calibrated Cepheids, and then we calibrate redshifts. We get what redshifts are, and supernova calibrates redshifts past that. So then redshifts tells us how to calibrate Hubble's constant. So this is, I think I've shown this before, this is a time-lapse photography of another type of object which is useful for determining distances, a globular cluster, and you see the variable stars there, the RR variable, RR Lyra, which helps us determine how bright those RR Lyras are, and therefore when we see them further out in the universe, we know how far away they are. And then supernovae take over from there, as we show here and here. We looked in previous lectures and so that this is a supernova that doesn't appear there. So we look for supernova in distant galaxies, particularly type 1a. and we see how bright they appear to get, and that tells us how far away those galaxies are. Sometimes there's lots of galaxies. So this galaxy, NGC 2770, had lots of supernovae in it. Here's a bright one being seen now. Here's one that faded. Here's actually another one. This one was in 1999. So this one was last year. This one was this year. So the last topic I'll talk about now is the age of the universe. So people have been trying to figure out the age of the universe since time began, since history's been recorded. There are several things that bound the age of the universe. The general thinking is that the universe must be older than everything in it. So however old you are, the universe is older than that. Your dad, your parents, older than that. Grandparents, older. Great-grandparents? Curious, anyone have any great-grandparents still alive? No? Oh, okay. Universe is older than they are. So you can ask them how old they are. Universe is at least that old. Turns out we can date the Earth. Rocks on the Earth. Their oldest rocks are about 3.5 billion years old. Universe must be older than that. Turns out we can find the age of the oldest white dwarfs by how fast they cool and things like that. 12.5 billion years old. Globular clusters by main sequence, by figuring out which stars are still in the main sequence in globular clusters. Haven't burned out yet. 14.6 billion years old, plus or minus 1.7. And this became strange because at this point, the globular clusters were getting older than we thought other indications of the universe was. So, for instance, if you just run the Big Bang back, you can get an estimate for the age of the universe, and that was coming in younger than globular clusters. But that was, here's white dwarfs. Here's some white dwarfs, all circled there. Here's main sequence fitting for the globular cluster, which tells us the old age. The answer was zoomed in on with the microwave background study that was shown in the very first slide, and is the last slide too. By studying the spot sizes on the microwave background, we can estimate how old the universe is. By how long it took from those spots to get to the universe we have today. And that also tells us a whole bunch of information, like what the universe is probably made of today, what it was made of, what type of matter it was made of back then. And so based on that, we can actually zoom in and now know for the first time, as of just a few years ago, in the lifetimes of everybody practically hearing this, we know the universe is 13.7 billion years old, plus or minus, 100 million years. And we've never known it that accurately. So now we know that, when we go back to previous slide, that these errors on globular clusters, we have to go to the early part of those errors. The minus is more important than the plus. And now the universe, knowing the age of the universe so accurately, we can go back and use that actually to understand globular clusters better. But I think it's spectacular that, in our lifetimes, we've now zoomed in on the age of this universe as 13.7 billion years. So here's a picture of the microwave background. If it had different spots, it might have told us. These are just, this microwave background, again, is about 2.7 degrees Kelvin. This is looking at it in one direction, picturing it on a sphere, and you're in the center of that sphere. Here it is in the other direction. Again, also 2.7 degrees, taking out the Earth's motion. These spots are very slight temperature differences. Let's go to a different color here. Very slight temperature differences in the microwave background. 1 part in 10 to the 5, as I was saying. Even so, this spot here is a little bit troubling, but even so, we understand these spots. These spots are not unexpected. They match a known type of universe that I'll be talking about next lecture. But even these very slight differences in temperature have been decoded to tell us that the universe is 13.7 billion years old. So we'll be talking more about the universe next time and reviewing the astronomy pictures of the day next time. So until then, see you. Goodbye.